السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى إن شاء الله زينين. محاضرتنا الحاضرة الخامسة لهذا اليوم هو spanning set. spanning set. definition. ناخذ تعريف. let S is equal to V1, V2 until Vk, V sub k be a finite set of vectors, vectors in a vector space, V, then span S is defined to be the set of all linear combinations of S. This is definition of span S. This set S, finite set, and this is definition of span set S. This is span V1, V2 and until Vk is equal to summation I is equal 1 to k Ci Vi. This is Ci and this is Vi, such that Ci belongs to R real numbers for I is equal 1 to k. This is definition of span set. If W is equal to span S, then we say that S is a generating set for W. And this is definition for span set, and this is important definition. Look, S is a set of finite vectors. V1, V2, this is finite until k. K may be 2, maybe 1, maybe 10, maybe 100, all, maybe everything. Be a finite set. This is have to be finite set of vectors in a vector space V. This is vector space and this is finite set subset of this is vector space. Then span S is defined to be the set of all linear combinations of the set of all linear combination of S, vectors in S, and this is in symbols, mathematical symbol, span V1, V2, Vk until Vk will be equal to summation summation I from 1 until k ci vi. ci تنتمي إلى belongs to R for I equal 1 to until k. If W is equal to spans S, then we say that S is generating to for W. That mean S generates W. S generates W. تولد in Arabic تولد. S تولد W. Because this is W comes from linear combination تركيبات خطية من عناصر الاس. linear combination يعني تركيبات خطية من عناصر ال W، عناصر الاس. ممكن أن ناخذ example. This is page number 1. ممكن أن نأخذ أمثلة حول هذا الموضوع. example. a line through the origin is spanned by its direction vector. Any line، أي خط، خط يمر من نقطة الأصل spanned by its direction vector، المتجه. أي خط يمر بنقطة الأصل يتولد من المتجه اللي يمر من خلاله، اللي بنفس الاتجاه ماله. أي خط يمر بنقطة الأصل يتولد من متجه يمر بنفس الاتجاه هذا الخط. أيضا example number 2. another example. a plane يعني مستوي through the origin is spanned by any two non-parallel vectors. parallel يعني موازي غير موازي. that lie تقع in that plane. that parallel in that plane. يعني المستوي اللي يمر بنقطة الأصل. أي مستوي يكون على شكل مستطيل أو مربع، أي مستوي يمر بنقطة الأصل يتولد من خلال two non-parallel vectors، يعني ليست متوازيين، يتولد من خلالهم يقعان في هذا المستوي. أي فيكتورين غير متوازيين يقعان في هذا المستوي راح يولدون هذا المستوي. أيضا ممكن ناخذ أمثلة أخرى حول هذا الموضوع. example آخر. let s is equal to 1 x square until x power to the power n. Then span S is equal to Pn polynomial order n. Polynomial order n. For example, span 1 x square. This is n here is equal to 2. Span is equal to ax square plus bx plus c, such that a, b, c belongs to R. This is real numbers, and this is equal to P2. This is polynomial 2, order 2. I think this is clear. This is span polynomial order 2. The set of all polynomials is spanned by 1 x square, x to the power 3, and so on. Polynomials mean متعددة حدود. Polynomials mean متعددة حدود. This is page number 2, and we can, of course, another definition for span set. Let S be a set of vectors. We say that S is spanned by a set of vectors B if and only if and only if each V belongs to S is a finite linear combination of the vectors in B. Moreover, given vectors V1, V2, until V sub k of the set of the same type span v1 v2 until v sub k is equal to w such that there exists ci such that w is equal to, this is element not set, this is element w is equal to c1 v1 plus c2 v2 plus until ck vk. And this is another definition of span. This is another definition of span. So we can define span set by the first definition. This is first definition on page number 1, and this is second definition. We can choose anyone. You can choose anyone. Here the same idea. S is a set vectors. We say that S is spanned by, here S is spanned and by a set of vectors of B. If and only if each vector in S is a finite linear combination of vectors in B. Any vectors in S can be written as linear combination of vectors in B. Moreover, giving vectors v1, v2, v until vk, the same type, this is the vectors the same. Span v1, v2, vk is equal to w. This is w if there exists ci such that w is equal to c1, v1, c2, v2 and until ck vk. This is we say that this is spanned, this set is spanned by V. Now take example, let W is equal to S plus T and 2S plus T and 3S plus T. Such that S T belongs to real numbers. This is set W. This is set W. Any number, real number in R, S plus T, and here 2S plus T, and here 3S plus T. We can show W is a subspace of R3 times 1, 3 rows and 1 column. And if we want to prove this set is a subspace of R2, we have to satisfy 3 conditions. The first condition, W is non-empty set. Of course, W is non-empty set because here take any real numbers in R, 1 plus 1, 2, and this is so W is non-empty set. Clear. This is clear. And if we take any 2 vectors here, also can be belongs to W. Here first condition, W is non-empty set. W is non-empty set because if we take S is equal 1, T is equal 1, so this is 2 and this is 3 and this is 4, this is belong to W, implies W is non-empty set. This is page number 3. And now we can prove satisfy second condition. The second condition number 2, let V1 is equal to S1 plus T1 to S1 plus T1, 3S1 plus T1, and V2 is equal to S2 plus T2 to S2 plus T2, 3S2 plus T2. This is both of them belongs to W. This is belong to W and this is also belong to W. V1 and V2. V1 and V2 belongs to W. I have to show that V1 plus V2 also belongs to W. So V1 plus V2 is equal to S1 plus T1 to S1 plus T1, 3S1 plus T1. This is plus V2 here, S2 plus T2, 2S2 plus T2, 3S2 plus T2. If we sum them, we get S1 plus S2 plus T1 plus T2 and 2 S1 plus S2 plus T1 plus T2 and 3 S1 plus S2 plus T1 plus T2. And this is the result. This is, look, this is first one and this is second one here. So this is 2 of this, 2 of this, and this 3 of this, and this is the same. This is by definition of W. This is by definition of W. This is S and T here the same, and this is 2 and this is trouble. This is couple and this is trouble of S. So and also S1 plus S2 belongs to R. Also T1 plus T2 belongs to R, so that V1 plus V2 belongs to W. And this is second condition. And third condition, we have to show that alpha, let V1 is equal to just V, we can take just V, V equal S plus T to S plus T, 3S plus T. This is definition of W. and alpha, this is belongs to W, this is belong to W, and alpha belongs to R. I have to show that V alpha belongs to W. We take alpha V is equal to alpha, this is out, and here V is equal to S plus T, and here 2S plus T, and here 3S plus T. 3S, sorry, here is 3S, and this will be equal to alpha S plus alpha T, and here 2 alpha S plus alpha T, and here 3 alpha S plus alpha T. And this is the same idea. Here alpha S and alpha T. Alpha S, this is couple of alpha S, couple of alpha S, and this is a trouble of alpha S, and this is the same. Alpha T, alpha T, alpha T. And alpha S belongs to R. Also alpha T belongs to R, so that alpha V belongs to W. This is page number 4. Then W is subspace of R31. Then, or we can say hence W is a subspace. This is subspace of R3 times 1. That's our problem. And now we can say this in subspace. This is subspace of R3, and this we can show that with the span. Let W, this element, belongs to W. This is set. Then by definition, there exists ST belongs to R such that W is equal to S plus T, 2S plus T, 3S plus T, and this will be equal to S, 2S, 3S plus T, and also this will be equal to, if we take S out, S here will be 1, 2, 3 plus, if we move here T, this will be 1, 1, 1. Look, so this is vector W is equal to S, any real number in this vector 1, 2, 3, and this is T in any one vector. Thus W belongs to span this set. span this set. 1, 2, 3. And this is 1, 1, 1. And it follows W. W is a subset of span these vectors. 1, 2, 3, 1, 1, 1. Any vector in W, we can make it by this is two vectors, linear combination of this is two vectors. So this is vectors span W. This is vectors span W. Any vector in W can be written as a linear combination of these two vectors. And this is W is a subset of this set, and conversely, if Y belongs to span this set 1, 2, 3, 1, 1, 1. If W belongs to this set, then there exists C1, C2 belongs to R. This is in R, such that Y is equal to C1, 1, 2, 3, because Y belongs to the set, span the set. So that means Y is a linear combination of these two vectors plus C2, 1, 1, 1. Because Y is a linear combination of these two vectors. But Y is equal to, that means Y is equal to C1, 2, C1, 3, C1, and this is plus C2, plus C2, plus C2. Move here and sum them. We get this. And this is clear Y belongs to W. We take Y here in this span set and we get Y is in W. This implies span this set is subset of W. Span, move another page. This is page number 5. This means that implies span 1, 2, 3, 1, 1, 1. This is subspace of W. So here you know in the foundation of mathematics in Usus Riyadiyat, W is a subset of span 1, 2, 3, 1, 1, 1. And this is the opposite side. span 1, 2, 3, 1, 1, 1 is a subset of W. So we get, this implies W is equal to span 1, 2, 3, and this is 1, 1, 1. So we prove that a W is equal to span these vectors. And this example is clear, I think. Now I think this is enough for today. This is page 6, and this is enough for today. Thank you very much.